Morning students, and welcome back to the Signal and Systems lecture. Today we'll talk about lecture 5. The topic of lecture 5 is on Fourier transform, and Fourier transform is similar to Fourier series except that it is applied to not just periodic signals, but it also applies to aperiodic signal. This is today's outline for our Fourier transform. First, you'll be introduced to Fourier transform, very similar to Fourier series again. And then we talk about the formulations of Fourier transform. There's some mathematics involved here, but fret not, because we have another one, the Fourier transform table, that I will show you that most of the time you don't really need to calculate using the formula, but you just need to refer to the table. And finally, we'll work on the Fourier transform properties, which is very similar to Fourier series again. The learning outcome for today's lecture will still be on LO2, which is to illustrate the applications and uses of Fourier transform in the analysis of signals and systems. So remember previously when we talked about Fourier series, we can change a signal that is from time domain into frequency domain, but that signal has to satisfy two things. The first thing is what you should remember very well, that signal must be periodic. So it should be signals that repeatedly every single period. Alright, so it must be periodic. Then the second one is a least common one, but it must be satisfied as well. When it is periodic, it must be square integrable, meaning that it cannot have signals that looks like this. So let's say this is also a periodic signal. Alright, this is also a periodic signal where it goes up to infinity and then comes back from negative infinity. Infinity, negative infinity is periodic, but then this is not integrable because the integrations will be more than will be at infinity. So we cannot have Fourier series of these systems. So let us ignore the second one, because second one you can't really find out anything about these signals. But let us look at how we can relax the first conditions, where it can we do something like to represent a signal in frequency domain when the signal is not periodic. So let's say we only have a signal. Let's look at one example on Fourier series itself. So let's say we have one graph or one signal that is periodically repeated, just a single rectangle signal that repeats every time periods of t. So this is the periods. And if you apply Fourier series, just use the formula that you learned in the last lecture to it, you will arrive at AK will be 2 sine of k omega t1 divided by k omega t. And then there is no bk because this is an even signal, bk will be all 0. So let us look at how we can plot these signals in frequency domain, where we need to plot this out. Okay, now let us see how we can plot this particular AK out, meaning that we are going to plot the signals in terms of frequency domain. So this axis is frequency, and the frequency is omega, so this is in terms of radian per second. And as we substitute different t into it, because at these original signals that is shown here, we did not specify what is the value for t. So let's say we give a few examples. When t is equal to 4t1, the first example, and then we substitute it back into the AK, and then we find out what is the value for AK, and thus we plot it out on the frequency graph, and we can obtain spike that looks like this. Alright, so you just ignore the curve over here. What we get is just the spike with all the different k. So AK equals to 0, AK equals to 1, AK equals to 2, so on and so forth. But what if we increase the distance between them? So this distance initially was 4t1, now it becomes 8t1. So we increase it. And when you increase it and you substitute it back into the same equations, you actually get different answers. So the answer you get is the spike will be forming a more narrow spike instead of a broader spike. So this one is still k equals to 1, k equals to 2, k equals to 3, k equals to 4, so on and so forth. And then if we further increase it, let's say to 16t1 now no longer 8 but 16t1, you'll notice that the spike is even closer than one another, where we have a very close number 1, 2, 3, and so on and so forth. So you'll notice one trend. Although we have a different period, alright, these three periods are totally different. They are a multiple of one another. But if you draw a curve forming all the peak of the spike, like this one here, alright, you draw this curve on each of the graph, you will notice that they are actually the same curve. And this same curve refers to A equals to 2 sine omega naught t1 divided by k, there's no more k, but omega naught t. So this curve is exactly the same as this one. So let us look at the next slide. And so if you think about it, if our t is getting further and further, and when t approaches infinity, let's say this was our graph, correct? And when t approaches infinity, meaning that the periods will repeat at infinitely long on the left and on the right. So this is negative infinity. And in mathematics, we write as infinity, but in real life, it means that this signals is not periodic anymore because this does not exist. Right? This one does not exist because it's at infinity and negative infinity. We can't really go to that point yet because it's an infinity. So this becomes an aperiodic signal with just a single square. That's all. There's only a single square for this signal. No more periodics. So if we apply the same concept when t getting larger and larger, we actually arrive at these equations where just now you have seen the plot. It is exactly this plot, which is the envelope of the Fourier series when t getting more and more. So now we have these new concepts called Fourier transform. So instead of calling it Fourier series, now it's Fourier transform, where we can also plot a single time domain signal into frequency domain. So let's say the time domain signal is this. So this is time domain. And if we plot it in frequency domains, we get a signal that looks like this. And this, notice that this signal is not periodic anymore. And we still manage to get frequency response. So this one is a frequency and this one is a time. So that is the Fourier transform for you. From the last two slides, you can roughly make a small conclusions on the similarity. Rather than I say difference between Fourier series and Fourier transform, I would like to talk about similarity between Fourier series and Fourier transform. Let's say, for example, you have a time domain signals. This is just example. It might not be accurate, but I just show you as an illustration. Let's say your time domain signals is a periodic signal that looks like that. And then if you Fourier series it, within your Fourier series, within your frequency domains signals, so this time and this frequency, it should looks like spike. So it should be something like this. Alright, this might not be accurate, but just illustrations. Alright, so if you have another signal that is just one period of it, so this is no longer periodic. It stops here, the signal stops here, no more. And we can still find out the Fourier transform in terms of frequency domains of this signal. And these signals will just be similar to the Fourier series of the periodic signals, but now all the dotted join up together. Alright, so previously we know it was here, right? So don't please ignore the green one, it's just for illustration. The green one is the Fourier series, and the red one is the Fourier transform over here. So that is a similarity between Fourier series and Fourier transform. But now we can treat every single signal, we just treat it as a repeated signal, and then we find out the Fourier series Then we join up all the dotted together. So we just need to just join up all the dotted together, and that become our Fourier transform. Alright, this one is the better illustration of what I just said earlier, because the drawing is much nicer than my own drawing. So initially, we have a single signus, single rectangular, which is obviously aperiodic. To find out Fourier transform, what we can do is that we assume that this signal is periodic, so we just copy and paste, copy and paste, copy and paste many of them. And then from here, we find out what is the Fourier series, which give us all the spikes. So the Fourier series, remember, Fourier series are all the spikes. And then now we just need to connect all the spikes together, like the dotted line here. After we connect it, this becomes the Fourier transform of that signal that is not periodic. Alright, so I repeat, this is the Fourier transform of a signal that is not periodic. So we can do it that way. Right, in the previous slide, you have seen the results of a square time input signals. After you apply Fourier transform, the results will be of a function that looks like this. And these functions exist quite regularly in Fourier transform, because all square wave will be transformed into this wave, and this wave was given by sine of omega divided by omega, as you've seen in the previous slide. So let us define this function as a new function called sinc. Alright, so this is a proper function. You can actually find this function everywhere else from the internet. It's not just for this course, but there is a sinc function that says that it is sine of certain values of the frequencies divided by that value. So this pi, whether is it there, it doesn't matter. It's just telling you whether this is in radian per second or in the degree. That's all. And for the sinc functions, it has a graph that looks like this. It is not exactly like sine graph, that it has a peak of 1 in the middle, in the when frequency equals to 0. Alright, the peak of 1 when frequency equals to 0 here. And then it will slowly go down at, it will cross over the frequency axis at 1, and then come back up, cross over at 2, and so on and so forth. So it will be like infinitely many ripples over here, and the ripples amplitude is getting smaller and smaller. Let us look at the mathematics of the Fourier transform formulations. And if you recall your Fourier series coefficients, you have these equations that you need to integrate through a time period. So remember, Fourier series, it must be periodic. So you can integrate it through this time periods. 1 period of it, of the original signals, multiplied by e power to negative j omega t. Negative j k omega t, alright, there is a k over here. So for Fourier transform, you need to integrate it from infinity to, or from negative infinity to infinity. So there's no longer a single time period because it's not periodic now. And this is just your normal functions, your signals functions, same as your xt, it's just right as vt over here. And e to the power of negative j omega t. There is no more k. So here is e to the power of negative j k and then omega t. Or sometimes I write omega in this way. And here is just e negative j omega t. And you know omega is 2 pi f. So if you see 2 pi f here, it's same as omega. So the formulation is basically the same. It's just that the integrations limits are changed from infinity, negative infinity to positive infinity. And there is no more k over here because this is no longer a discrete function. With Fourier transform, we can also do the inverse of it, meaning that let's say if we are given again a rectangular signals, if we do the ft Fourier transform, you will obtain the sinc graph, correct? And now what if you are given only the sinc graph, and you need to do the you need to find out what is the time signals of this. So I'm telling you that I'm giving you a frequency domain graph and it looks like this, and now you want to find out what is this signals in time domain. So this way we need to do the so-called the inverse Fourier transform. It's just the opposite of Fourier transform. The formulas looks very similar, so it's just this will be your signals in frequency domain multiplied by e power to j omega t or j 2 pi ft, and then your df from negative infinity to positive infinity, and there you will be able to find out the inverse Fourier transform of the signal. So you'll notice that here sometimes I write Vf, so this is a bracket, Vf as your signal in frequency domain. So these are frequency domain signals. Sometimes you might see V omega as your signal in frequency domain also. So just take note that this is just different scale, that's all. So remember 2 pi f will be equals to omega. They are both explaining the same thing, except that one will be, the axis will be frequency, the other one, the axis will be radian per second. So this one will be in hertz. And then for these inverse formulas, you might sometimes also see this case, positive, negative, infinity to infinity, V omega E j omega t d omega is also possible. It's the same. It's just that one is dealing in hertz and one is dealing in radian per second. They are exactly the same. Alright, so take notes also, this formula is slightly different from the Fourier transform, that there is no negative here. Alright, remember in Fourier transform there is a negative sign at this point. And this slide shows properties of the spectrums of the signal. So when I talk about spectrums, frequency spectrums of the signals, it means that how the signals behave in frequency domain. So this will be the frequency domain, and just now you still remember the sine graph. Let me draw it out. Alright, this way. And you have learned these properties actually in your second lecture, where you learn about different way to represent signals in frequency domain. And one way is to represent it in terms of magnitudes and angles. So let me write here, this is the magnitude and this is the angle. And remember, the examples given, when you represent it in magnitudes, it looks something like that, correct? And this is frequency. When you represent it in angles, it looks something like that. And this is again in frequency, and this is your angles. And I have already told you also that in this frequencies spectrums analysis, the magnitude, so this one is magnitude and this one is the angle, the magnitude is always even symmetry, meaning that the left side and the right side will be exactly the same. And the angles will always be odd symmetry, meaning that the left side and the right side will be reflected on the x-axis. So please recall this. If you cannot recall, please refer back to the lecture 2 or lecture 1, one of the lectures that talk about properties of these frequency domains, frequencies analysis. So this basically talk about the same thing. When you Fourier transform a signal, that then you draw it out in the frequencies domain, your magnitudes will be even symmetry. So V negative omega will be V of omega, alright, the magnitude of it. And the angles of it will be odd symmetry, meaning that the angle of V negative omega will be the negative angles of V omega, as shown in these two small graph over here. Let us look at this example. Let us try to solve it together over this slide by using the formulas of Fourier transform. So this is the usual examples I always give is a rectangular signals. We decide from negative a to a, and then if you remember, if you want to work on the Fourier transform, so this xt, so at the end of the result it will be x omega will be equals to negative infinity to infinity. You need not to memorize this formula because it will be given in your test, and then this is e power to negative j omega t dt. Alright, now if you look at this particular graph, everything that is above a will be 0, correct? Everything below negative a will also be 0. So when you integrate the signal over from infinity to negative infinity, everything else is 0 except at this point. Alright, except this point is not 0, but at this point is a 1. So you see it's a clear constant of 1 at this point. So we are able to shift the limit to just negative a to a, where x is 1, e power to negative j omega t dt. Alright, now let us try to handle this integration. And I've given you clue over here. And again, most of the integrations table will be integrations of variables will be given inside the integration table. Please refer to the table that I've uploaded on times to see whether the formulas that you are not familiar with are they in the table. Alright, so let's say this is a formula of integrate of at. So we have to just do exactly the same thing. It will be negative 1 over negative j omega, and this will be e negative j omega t, and the limit is from a to negative a to a. Alright, any problems here? No problems, right? And now if we substitute the limits into it, e 1 over j omega, and this is e of negative j omega a minus of e of j omega a, because now you substitute a negative a into t, and negative with negative will give you positive here, and then we can write it as, oh, there's a negative here, okay, don't forget. So we can make it positive. So how do we make it positive? So you just multiply by negative 1 here and multiply by negative 1 on this side. So you get 1 over j omega e j omega a minus e negative j omega a. And now you notice that one thing that's very obvious here, which is this particular, I will write in the different color, 1 over j, or 1 over 2j, and then I multiply a 2 on top. Alright, then e power to j omega a minus e power to negative j omega a will give you a sine of omega a, correct? And remember, you have to multiply back this 2 on top and divide by this w at the bottom, or omega, not w. So that is your answer. You can leave it this way, or you can just write as 2 over 2 pi f, if you like an extra step, up to you, sine of 2 pi f a. And then you cut off the 2, so become 1 over pi f sine of 2 pi f squared a. And let us look at the final answer, which is correct. Alright, the final answer has also do another further step, which is to change it to sinc signal. Alright, for you, I do not request you to do that. Alright, you can change it to sinc signal if you want, but if you leave this as the final answer, or even you leave the omega as the final answer, it's fine, it's good enough. Alright, because sometimes sinc signal is not very easy to be visualized because you are not used to it. You are used to sine signal but not sinc signal. And sometimes it is quite difficult or tedious for us to do the integration, especially if your signals is not just a square signals. Let's say your signals is something like sine signal, and then imagine you need to sine signal multiply by the exponential signals. Alright, I write it here. The formula was xt multiplied by e negative j omega t dt. But if your signals is, let's say, a very complicated signal, you have sine of omega t, then multiplied by ej omega t. This is very complicated when you want to do the integration, although the formula will be given to you. Alright, it's still complicated. So there's one way that people has found out. What do they do is that they actually find out the Fourier transform of a few examples of signals, and then they tabulate it. Alright, so we only look at the Fourier transform here. Okay, we can ignore all the Fourier series at the right side. Alright, in Fourier series, if you want to refer to the table, you can, but Fourier series is easier to solve using the formula. The table is very complicated. So you look at Fourier transform. This table has many things that you might not even use, so you just need to identify a few that you usually will use according to your tutorial questions or according to the examples in these lecture notes. So one will be this one, equals to 1. And then cosine and sine also quite useful. E to the power of j omega t also useful. So it means that, let's say if your time domain signals is cosine omega t, is something like that, and then what is your Fourier transform of it, then your Fourier transform will be exactly this one. So you don't have to work on the integration here. You no need to work on the integration here. You can straight away write the answer as this one. Alright, same thing with sine, same thing with xt equals to 1, and then you see this is the square wave. Alright, so you can just ignore the word periodic because this periodic square wave is for Fourier series, but for Fourier transform you don't need it to be periodic because you don't really need t over 2. You see your formulas. Okay, the formulas here is not really in Fourier transform. Let me look at the next slide. Okay, yes, so that is the same signal. So previous slide, that one you can just ignore it because it is only for periodic signals. So for non-periodics, if you have a rectangular wave, this is a rectangular wave. So at this origin is 0, and this is t1, and this negative t1, and this the magnitude is 1, and you will get this expression, which is what you did just now. Remember, you did this 2 omega sine of omega t. Alright, so now you can just refer to the formula. And then here also, if you have the signals on the other side, you actually get back to the a square wave on your frequency domain. So remember, this is time domain and this is frequency domain after you do your Fourier transform. And then if you have a spike signal in time domain, meaning that in time domain your signal is like that, the spike at 0, then in your frequency domain is just a constant 1. If you have a step signal, then in frequency domain you'll get this. Alright, so just take a look at the table, and then the best case is to refer to your tutorials and examples as shown in this lecture, and then try to match the tutorial questions to all these time domain signals that you can find, and then try to find out what is the answer within the table itself. If you cannot do that, then you have to use the formula. You have to do the integrations of xt e power to negative j omega t of dt, negative infinity to infinity, which is quite tedious. And this is the final section of the topic where we learn on the properties of Fourier transform. And these properties, like I said earlier, properties of Fourier transform will be same as properties of Laplace transform or Z transform that you will learn later. So everything will be just repeated. They will have the exactly same properties because each of them are the signals represented in frequency domain, although you use different methods to represent it. So let us look at the first properties, which is the superposition properties. It means that the systems, when you have a time domain systems, this is a time domain, multiplied by a constant, plus another time domain system multiplied by the other constants, it will be equivalent to having the frequency domain of that signal multiplied by the same constant A, plus the frequency domain of the other signals multiplied by the same constant B. So this one we call the superposition principles, which means that this Fourier transform is linear. Alright, this is actually the linearity property as well. And for time scale of your time domain signals, let's say your time domain signals is scaled up by A. So the time scale is scaled by A. So it means that your frequency domain signals will be scaled down not only on the frequency itself. So first, the frequency is scaled down by A over 1 over A. And the magnitude also scaled down by 1 over A. Alright. The next one is the time delay. If you have a delay on your time domain signals, delay of t naught, it is just equivalent to your frequency domain signals multiplied by the e power to j omega t naught. Alright, so this one is just omega t naught. And this delay says that in a signals that has delay, the frequency of it does not change because this is exactly the same. But the phase will be changed by the t naught, omega t naught of your delay. Alright, so the phase of the system will change, but the frequency will not change. Now for frequency shift, so this is like the opposite of it. So if you have a frequency domain, when you shifted your frequencies, in your time domains is just the original time domain signals multiplied by ej omega t. And this is one example that we can make good use of frequency shift in our communications module. So sometimes when you have a certain time domain signals, in frequency domains, it will span through the zeros, negative omega, and positive omega. Because of the properties of frequencies domain, it will be even symmetry, meaning that those on the left will be same as those on the right. But which means that it limits our bandwidth to just the omega. So let's say sometimes we want a higher bandwidth for our signals to be sent through. What we can do is that from our time domain signals, Vt, from our time domain signals Vt, we just need to multiply it by e power of negative j omega, and this omega will be the omega c, which is the 2 pi fc. E power of omega j e power to omega ct. And then when we do the frequencies Fourier transform of it, we'll get the exactly same shape in terms of frequency response, but now it is shifted away from the zero. So if you draw it, extend it on the negative side, you will also see the same thing on the negative side. But now we can ignore that things on the negative side, because with this itself, we are able to reconstruct back our original signals easily. The next property is the modulation properties, where when your signals is in time domain is multiplied by a cosine of omega t, then your signals in frequency domain will be divided into two parts, where one part will be of the frequencies that is shifted to the left, and the other part will be frequency of that signal shifted to the right. So this is called the modulation property. You don't need to memorize of all these properties over here. It's just for your information. And then if you multiply by a cosine signal that has a phase change of, let's say, sometimes I write theta, but in this case it's a phi, but just treat it like a theta. And then you will have your frequencies domain shifted, again one on the left and one to the right, and each of them will be suppressed or will be amplified by the phase change. One example is how we could make use of the modulations property to solve a Fourier transform problems easier. So let's say we have a signals that is a rectangular signals multiplied by a cosine signals itself. So the signals will look like this. It does not continue. It does not continue over here. It just has the envelope over here because it's a rectangular signal multiplied by a cosine signal. And that rectangular signal has a limits from negative tau over 2 to tau over 2. So if you want to do this for Fourier transform, it's very tedious because you need to multiply by e power of j omega t and integrate it from negative infinity to positive infinity. But now we know that when we have these cosine terms here, we can actually ignore it first, and then we find out the Fourier transform of these terms in front of the cosine terms. So let's say this terms is z prime of f or omega after you do the Fourier transform. What you need to do is that you just need to use the modulations properties to shift this become a over 2 z prime of f minus the fc plus a over 2 of z primes of f plus fc. Alright, so this is to make use of the modulations properties. So therefore, after you substitute everything into that zf, you will have this. So this is actually the z prime f minus fc, and this one is a z prime f plus fc. Alright, and you'll be able to easily get the amplitudes of your frequency domain easily. Alright, without really solving a complicated integrations. Next is the properties of duality. Duality is a more important properties. It means that, let's say, if you are transforming a signal from time domain to frequency domain, and then now you want to transform that signals. Now, if the signals of time domain and frequency domains are swapped, alright, so let me give you an example. So let's say you know that this one will transform frequency the Fourier transform into the sinc signals. Okay, you should be very familiar now. But what if now in time domains you are given a sinc signal, and then I ask you to transform it to frequency domain? And these duality principles has tell you that the transformation is the same, except that the frequencies will be negative. So it will still be the square signals, because for square signals the frequency in the front and frequency at the back is the same. So even though if you transpose it, it's still the same. Alright, so let's look at the next slide for example. So this is the examples that I shown earlier. If you have a square signal, you Fourier transform it, it will be a sinc signal. And this one, why is it all positive, is because we are only looking at the magnitude. Alright, so initially it was negative, positive, this way. Alright, negative, positive, positive. But now we are only looking at the magnitude. So we just reflect it when you have the modular sign. Okay, so now given in the time domain, if your time domain looks like a sinc wave, or it is a sinc wave, when you do a Fourier transform, it will be the same. It will just be a square wave, as if you are doing the Fourier transform earlier. Alright, so this is called the duality's properties. The differentiation properties. If you differentiate a time domain signals in frequency domains or in frequency domain after you do the Laplace transform, it is just a multiplications to j omega of that signal itself. So if you differentiate it n times, it's just the j 2 pi omega power to n, or j omega power to n, or j 2 pi f power to n. So this is a very simple properties of differentiation. Differentiation, it will be the opposite of integrations. So instead of multiply by j omega, you are dividing it by j omega. But take note that when you do integrations, you will be left with a constant term. And these constant terms, most of the time we can assume it as 0, because most of the time at frequency zeros, the signals will be 0. But it will be depending on your application as well. So please do take notes here. Finally is the convolutions properties, or convolution and multiplication properties are same. Alright, so convolutions is telling us that, if you still remember what convolution is, convolutions will happen when you have signals in time domain passes through a impulse response of the systems in frequency domain, in times domain, and the output will be xt convolutes with ht. And if you remember chapter 3 well, the convolution operator is very hard to compute because you need to do integrations as well. But now this convolutions theorems or multiplication theorems is telling you that this convolutions is actually equals to x of f, or x of omega, multiplied by h of f, or h of omega. So what we can do now is that instead of passing it the time domain, the signal in time domain, we find out using the Fourier transform to find out the frequency domain signals to pass through the frequency domains of the impulse response of your systems, and the outputs will be just them multiplied together. So now you don't have to do the integration anymore, you just do multiplications. So the same things will happen on the other way around. If you need to do convolutions in frequency domain, it is equals to multiplications in time domain. Alright, so I shouldn't write the equal sign here. It's equivalent to multiplications in time domain. So sometimes we can play with it. Whenever we want to do convolutions of two different signals, we do Laplace transform, or we do the Fourier transform first on the two different signals, and then we multiply them together, and then we do an inverse Fourier transform. And most of the time we can refer to the table to do Fourier transform and inverse Fourier transform. So that will help us easier to do convolutions operation. And this is the summary for today's lecture. It is quite short because much of the things are similar to Fourier series, except that this Fourier transform, in summary, is to find the frequency response of a system or signals that is not periodic. And most of the time, we just need to refer to the Fourier transform tables to obtain the results of the Fourier transform. But if you cannot do that, or if you can't find the results from the Fourier transform table, you can still do integrations following the formula shown here. So this is the Fourier transform formula, and this one is the inverse formula. And then we also learn of the properties of Fourier transform. The properties that you really should take notes is the convolutions and multiplication properties. So it says that any signals in time domain, when it's convolutions, let's say to yt, it will be equivalent to, in frequency domains, multiplication. Alright, and vice versa. If its frequency domain is convolution, then in time domain it will be multiplication. So for the next lecture, we will talk about discrete time Fourier series and discrete time Fourier transform. Again, this is a subset of what you have learned these 2 weeks, except that this discrete time, well, the name itself already infer, it applies on discrete signals. So in the Fourier transform or Fourier series, let me draw it here, Fourier series or Fourier transform, if you notice, your time domain signals is always continuous, whether it's periodic or aperiodic. If you have a time domain signals that is discrete, let's say this kind of signals like that, what do you need to do? So that is where you have to apply discrete time Fourier systems, Fourier series, and discrete time Fourier transform, which you will learn next week. So I will see you again, and thank you so much.